Lecture 17. In this lecture, we're talking about doing math in assembly. Yay, math! We all love to do math. Yay! Well, okay, anyway. So, the question is, why do math in assembly? Well, one reason is speed. So, that's important. It's helpful to be able to do things faster. Intensive things can happen quicker. As you can see, it's all about speed here. That's the issue. So that's one of the reasons we would use assembly, is that it can do things more efficiently than can be done in C. In C, there tends to be quite a bit of overhead associated with various things, and if we can do it simpler and streamlined, that can help things. So in particular, this can be helpful in things like filtering, digital signal processing, controls, image processing, and so forth. So those are specific application areas. Now, in our discussion of math, we're going to look at the math we can do. Okay, so there's a lot of stuff that we're very limited in. There aren't any built-in functions like sine and cosine and exponential and all those kinds of things. Even just very basic math is very rudimentary. So we're not likely going to do very advanced things like solving differential equations or taking Laplace transforms or anything like that in this. We're going to be doing things like add, subtract, multiply, and divide. Okay, so that actually can get us pretty far in a lot of things, but it's not all automatic. Then we're going to look at something like taking the roots, square root, cube root, those kinds of things. Then we're going to look at using integer ratios. Integer ratios in terms of working with constants, but also integer ratios in terms of various kinds of functions that could be executed. And finally, we're going to just very briefly touch on floating point calculations. Floating point calculations. So that's a very deep subject. That's well beyond what we want to get into. But our Arduino, the ATmega 328P microcontroller, actually has some rudimentary floating point calculations. So we're going to take a look at those and see how to use them. So at least we can use what's available to us. Okay, in terms of math background, it's helpful to understand the differences between integer calculations and floating point calculations. It's helpful to understand the concept of fixed precision math and efficient calculations and calculated risks. Now, as we go through here, for the most part, we're going to be doing integer calculations. We're going to eventually talk about some floating point calculations, but basically we're going to be doing integer calculations. And so when we work with integer calculations, we have the two options: the int, that's an integer, and the uint, unsigned integer. And that kind of thing is going to keep popping up, rearing its ugly head, those differences, because they're two different kinds of number representations. So it's very common to want to use only uints, unsigned integers, in the calculations. Why? Well, for one thing, the functions associated with them are more efficient. We can talk about things like modulus arithmetic. That's well defined. We can talk about an overflow of unsigned data, and then that is well defined. Shift operations on unsigned data work for multiplication or division. And register contents within the Arduino are pretty much always treated as unsigned integers anyway. So if we only worked with uints, that would be a good way. But unfortunately, we can't always, and we don't always want to. There are times when we definitely want to use signed numbers. Okay, so we'll start with addition and subtraction of integers. So adding or subtracting a 1 from a register, we can do easily using increment or decrement. So that's the easy one. Requires one operand, and it works with all registers. Adding or subtracting a constant from a register, however, only works register 16 to 31. So that's that upper register. To subtract, we would use, if I want to subtract immediate data, I use sub I. For example, like this, I can add 2 to register 16. To add, we need to use sub I. There's no add I. There's no add immediate data. There's only subtraction of immediate data. So how would we use sub I? Okay. The other thing we need to check whenever we do adding or subtracting is we need to check for a negative or an overflow that results. So it's simple enough to add 2 1-byte numbers. We just load the 2 registers with the values we want, then add or subtract. Okay, so here's an example. I'm loading this value into register 18, this into register 19. Notice this is an alternate way of expressing a hexadecimal number, and then we subtract the 2 numbers. So, in general, like integers only should be added or subtracted. So that is a uint 8 with a uint 8, or an int 8 with an int 8, etc. So that's the general rule. And if you can follow that, that's great. If you need to add mixed integers, this quote-unquote standard approach is to convert the int, which is signed, to an unsigned int, and then when you do the addition or subtraction, the result ends up being an unsigned int. Okay, so incidentally, this whole concept of adding and different data types or subtracting different data types is a problem not just in assembly, it's a problem in C. You can find page upon page in the internet talking about this whole problem of mixed integers, signed and unsigned. So it's definitely an issue, and there are lots of weird things associated with it. Sometimes it's necessary, but you just need to be very careful when you do it. Keep track of what was positive. So if your signed int is negative and you're adding it to a positive, well, an unsigned int, then you just need to recognize that you're actually doing a subtraction and so forth. So you just need to exercise care in that. So what about adding now multi-byte constants? So in general, we would define registers for each of the bytes required of each addend or minuend and or subtrahend. That's kind of a weird thing, isn't it? These math terms that they throw to describe the different parts. So addend are the 2 things that you add together, those things. The minuend in a subtraction is the thing that's getting subtracted from. The subtrahend is the thing that's getting subtracted. So A minus B, A is the minuend, B is the subtrahend. So anyway, new words. You get a vocabulary lesson today too. All right, add or subtraction commands basically you would use on the low byte of the data, and then that in general may set the carry bit, in which case then you would use the add with carry or subtract with carry on the following bytes in successive order. So you start with the low byte first, and the next byte, and so forth, all the way up. If you're working with immediate data, then you may use subtract immediate or subtract immediate with carry. Now we move on to talk about multiplication of integers. So we've done subtraction, addition and subtraction, fairly straightforward. We've actually done some of that in some of our programs. Now, notice this little guy over here. Unsigned. We need to think very carefully about whether we're working with signed or unsigned numbers. So I'm just going to put a little marker off to the side here to indicate whether what we're working with are signed or unsigned numbers. What happens to the size of the result when we multiply 2 bytes together? Okay, so here's an example. I have this binary number. I'm going to multiply by this binary number. So it's, again, these are integers, so we don't have to worry about decimal places. So this number is 223, that's 247. When you multiply these 2 numbers together, you can go through and show that this is the result you get. Look how many bits we get. So in general, an 8-bit, when we multiply, will give 16 bits. in general. Okay, so that's an important thing. Now again, if you're working with unsigned integers, multiplication by a power of 2 basically corresponds to a shift. So when we multiply a number by a power of 2, that's equivalent to shifting the multiplicand to the left by the power of 2, keeping track of the number of shifted out bits. Okay, so this product, so notice I have a 1 and then these zeros, that's a power of 2. Basically that corresponds to adding these zeros back behind this number. So I've shifted them out. So in this case, I can shift. So if this is 7 to the 7, I can shift 7 times and just keep track of each time as I shift the bit that comes out. So that's one way. That's a very simple way of doing a multiplication, is doing a shift. So powers of 2, multiplying, easy. You shift it to the left, add zeros. So in this case, we can use the LSL or the ROL commands in doing the shifting. So here we would focus on the LSL. Looking now, we can see how to multiply 2 single byte unsigned numbers. So basically we use the mul command, which operates on all 32 registers. So I can multiply any register by any other register, and the result goes in registers 1 and 0. Incidentally, because of the fact that it actually goes into registers, part of it goes into register 1, generally speaking, after you're done doing a multiplication, it's good to transfer this data out of register 1 and clear register 1 so that register 1 is the 0 that it's supposed to be. Right? Remember, register 1 is supposed to be 0? Well, here it's an application where it's not 0, and so you need to clear it. So anyway, you multiply the two numbers, the result goes into registers 1 and 0. So, simple enough. Now, what about multiplying two 2-byte numbers? So here's my 2 bytes. A, byte 0, A, byte 1. A, B, byte 0, B, byte 1. So if you think about what's involved in multiplying this out, okay, so this would be great fast group work, but if you're working in a group. So if you think about what's going on here, so I first multiply the 0 bytes together, okay, so that's in general going to give me a 16-bit number. All right, because that's whenever you do a single byte multiplication with a single byte, you get 16-bit number. So this is really a 16-bit number. Okay, and then I'm going to multiply this byte by that byte, and then this byte by that byte. So B0 times A1 is this, and notice I need to put here, I say 0, but that's actually a set of zeros. Okay, that's actually going to be a set of zeros. That's going to be 1 byte worth of zeros that needs to be put there. So we need to keep track of those zeros. Similarly, when I multiply these two guys together, those also are going to have the same number of zeros behind. And then when I multiply the high bytes together, I'm going to have to add additional zeros on. And so we get a result like this. And so when I'm all done, I add up all of these 4 terms, and that gives me the overall sum, which looks like this. Yowza. So this 2 to the 8 means it's shifted over. There are 8 bits that's shifted over. This one is shifted over by 16 bits. So this quantity is a 16-bit. It's a 16-bit product and it's shifted over by 16 bits. So you can see the end result can be as high as 32 bits, which is what we would expect. 2 bytes. So 16 bits by 16 bits should be 32 bits. So that's important. Okay, so this is the process that we would go through in terms of multiplying two multi-byte numbers, two 16-bit numbers. And we could do that using this kind of a command. Here I'm loading register 16, 17, 18, 19 with so these two are one set of numbers, these two are another set of numbers. Okay, and I'm going to use register 2 as the 0 placeholder. So this is a high byte, that's the multiplicand. The multiplier is the low byte. This is A and this is B in terms of numbers, as we had before. So we're going to clear R2. I guess we don't need to clear it twice. We're going to now do this multiplication. So this does a multiplication. So here, I notice I only specify, here I'm multiplying the high bytes together. I'm moving the result. So remember that when you do move W, that's actually moving words. It takes the low byte from each register pair. So this is putting registers R1 and R0 into registers R23 and R22. Again, it's specified by their low bytes. So I first multiplied the high bytes together. Now I multiplied the low bytes together. Okay. And again, I shift that over into registers 21 and 20. Now I'm going to multiply the high byte of A by the low byte of low byte of B. And I'm going to add the result to the answer. So here, the answer really, so this is a 16-bit multiplication. The result is going to be put into registers 0 and 1. So I'm going to do the low byte, and I add that to the result that we got here. So remember, this is when it says move W, it's actually registers 21 and 20. So it's actually putting that into the low byte. The low byte of this product is going to go into the high byte here, and then the high byte is going to be at the carry for that is going to go here. Okay. Now we've already done this multiplication, and so we're going to add that onto this multiplication result. Okay. So we've actually done 3 multiplications, 3 of the 4 multiplications that are needed, and we have updated everything up to that point. And finally, we multiply this product together, the high byte and the low byte, high byte of B, low byte of A together, and then we do the same kind of thing in terms of putting the pieces in the right places. And again, you need to add with carries when you do some of these things in order to make sure that when you do the addition, all the addition is being done properly. Okay, so if you multiply two 16-bit numbers together, you get a 32-bit number. What happens if you multiply 32-bit two 32-bit numbers together? How many registers are actually required to do this? Which registers should be used for what? And is this even a worthwhile thing to do? So, good questions. Things to ponder. So, we've been focusing now on unsigned multiplication. What about signed multiplication? Well, we have this command, muls, multiplication of 2 signed numbers. So I can use any register, RD and RR, so these are the high registers, 16 to 31. Again, the result is stored in registers 1 and 0. This affects only the carry bit and the Z bit, and we would use it just like this. So it's used pretty much just the same as mul, except now it understands signed numbers. What about mixed sign multiplication? So mul SU is mixed sign multiplication. Mul SU, so it takes two registers, destination register and a source register. these registers must be between register 16 and 23, which is kind of a weird deal. So it doesn't go all the way up to 31, it only goes up to 23. So these registers need to be very specifically assigned. And in particular, the destination register must be assigned the signed number, and the source register must be the unsigned number. So we have mixed, but you have to put them in the right order. Okay, so you have to keep track of which one is the signed, which one is the unsigned. So unlike most multiplication that's commutative, it doesn't matter which order you multiply them in. This signed number multiplication is not commutative. It does matter which order you multiply them in. Again, the result is stored in registers 1 and 0, and again, this affects only the C and the Z, right, S register bits, carry and the Z bit. So here is a routine that does a 16 by 16, a 16-bit by 16-bit multiply, and so you can see it's actually fairly straightforward compared to some other multiplications. So we can see that we have a moles S, a mol SU. So we have a number of things going on here. So a mol signed, a mol unsigned, and a mol mixed multiplication. So we have all three of those multiplications going on in this particular subroutine. So that's the multiplication. So we've done addition, multiplication, subtraction. Now we move on to division. When we think of dividing a number by a power of 2, that is equivalent to shifting the dividend to the right by a power of 2 and then keeping track of the shifted out bits. So for example, 223 divided by 2 to the 7, we shifted over 7, the decimal place, we shift over 7 bits, and so this is the result that we would get. Okay, so we need to think of it that in terms of that. Okay, and again, we would use the LSR and ROR commands. So the L commands, LSL. I'm sorry. We're doing shifting right. So we're going to use the LSR, not LSL, and ROR. So it's right. It's all going right. Now, when you think about dividing any two integers, how many decimal places are needed to keep track of the result? Well, if you think of the number 1/3, 1/3 is 0.33333. Okay, and goes on forever, right? It's a rational number. A rational number in general can have repeating decimal places, but they go on forever. So we don't really necessarily want to keep track of division of integers by keeping decimal places. Instead, a more straightforward way of doing division is to do it this way. If I think of a numerator divided by a denominator here, okay, so we can think of it as the quotient and the remainder. Okay, so the quotient is basically such that this number r, the remainder, is less than this number d. Now, this quotient or this division, if n is less than d, then the result is that q will be 0 and the remainder will be n. So when n is greater than d, in general, we will get an integer quotient and an integer remainder. Okay, so this is more straightforward. So here, 1/3 would just basically be of this form, still be 1/3. But suppose we had 10/3. 10/3, we would get 3 plus 1/3. So at 3.3333. And so we would have 3 and then 1/3 here. Okay, so that's a more straightforward way, and so that way we don't have to keep track of an infinite number of decimal places. So this is the plan this is the approach we take. It's fairly straightforward. And so the question is, when we do this division, what do we want? Do we want both? Do we want Q? Do we want R? Or do we want both of them? So remember, if you have a function, you get one thing returned. Okay, so which one do you want? Okay, so generally speaking, Q is usually, well, the quotient. The remainder is this quantity, or n mod d. Okay, so the modulus is what we get when we do R for unsigned numbers. So in general, however, to get Q, one way to get Q is to keep subtracting d from n until we get a negative number. So there you can think in terms of a loop. You just keep subtracting d from n until you get a negative number. The number of times we subtract before getting a negative is the value Q. So in other words, the last time you subtract and you got a negative doesn't count. Okay, you count all the ones until you got a negative, before you got a negative. To get the remainder then, once you have Q, the remainder is equal to n minus d times Q. So this is the number of times, Q is the number of times d, and so this better be a positive number. Okay, and so this is the basic approach we would take in doing division. And so you can see, to do division, basically we can do it by iterative subtraction. So you can see, in terms of calculation time, division takes longer than either multiplication or addition or subtraction. In fact, it can require quite a bit depending on how big of values these are. So this works for multi-byte numbers as well. So in other words, the R, the N, the D, and so forth can all be multi-byte numbers. So that's helpful. Now, when you do division, if these are, for example, bytes, N is a byte, D is a byte, when you do this division, there's no way this number is going to be greater than N. It's going to be less than N. So in that case, Q will always be a byte. Okay, it doesn't have to be. Unlike multiplication, that when you multiply together it expands. Actually, when you do division, it contracts. So this will still be a byte, even though these were bytes, and this will be a byte, but it'll never expand beyond a byte. It'll always be less than. And when you do multi-byte numbers, you can go through and show that that the result will generally occupy less number of bytes than the original numbers that we're working with. So it can be. So of course, if D is 1, then you'll always get the same number of bytes over here as you do. So you have to assume that the result will, in general, be the same same number of bytes or less. The result will always be the same number of bytes or less as the thing you're dividing by. Also, the other thing, of course, you always need to check whenever you're doing division is, are you dividing by 0? Okay, that's always a no-no. But since you're doing the division and you're here, in a sense, doing it by hand, you can always check to see if the denominator is 0 or not. So this is the division process, and it would be good to go through and derive subroutines to do these kind of math calculations. So in general, it's helpful if you're going to be doing much math programming to actually write subroutines or functions to do multiplication, division, subtraction of large numbers, and so forth. Of course, subtraction and addition of large numbers, it's hardly worth, by the time you set it up and you pass it to the function, you really haven't saved much. If you're going to do that, it's helpful to document the subroutines well. So this is an example: signed to multiply of two 16-bit numbers with a 32-bit result. Okay, here's the usage. Okay, the contents of registers 23 and 22 and 23 are multiplied by the contents of registers 21 and 20, and the result goes in registers 19 down to 16. Okay, so that the user knows exactly where to put stuff and where it will be returned to. So this is, notice, this is just a subroutine. This is not a function. Okay, so you could also define a function, in which case you know exactly where to put the parameters that are being passed. Remember, the high byte goes in register 25, and then they go on down from there. Okay, so you could also do it by way of using a function and a function call. So that would be one way of doing it. Right? So some things to think about. But planning ahead and having subroutines so that you have a nice modular package can very greatly simplify your code. So you can go through, you can set up this multiplication routine, you can check it to see that it's working properly, and then you just have that code. And now you hang on to that code, and you can maybe put it in a file somewhere, and when you need it, you can just copy it and paste it in your program and then just call it. Simple. So, good thing to think about in terms of planning for your programs. So, that's division. So notice I'm not giving you actual algorithms for division like I did in some of the other cases, because you can see that it becomes a little bit more complex. But actually, I'm going to let you do this in your group work. Next, we move on to talk about roots of integers. So, when we talk of roots, first thing we come to is square roots. And it turns out here are some properties of squares. 1 squared is equal to 1. 2 squared is equal to 1 plus 3. 3 squared is equal to 1 plus 3 plus 5. 4 squared you can go through and show is 1 plus 3 plus 5 plus 7, and so forth. You can go through and show that the square of an integer, n, is the sum of the first n odd numbers. Okay, so the integer portion, s, of the square root, then, can be found by successively subtracting the odd numbers. The value s, then, can be found as the largest number of odd numbers that subtracted does not give a negative number. So it's similar to division. It's actually quite similar to division. So we just subtract odd numbers instead of just subtracting the same number over and over again, like when you're doing division. Here we're subtracting the odd numbers. So we start with 1, 3, 5, and so forth. Okay, so very straightforward for square roots. So square roots are really easy. Of course, if you need to do the fourth root or any even root, you can just repeat this process. So you take the square root, they take the square root again. Again, all of this is very straightforward if we have signed numbers. If we have unsigned numbers, then we have to check to see if we have negative. We have negative, we have to worry about how do we represent complex numbers, and things get more complicated if you used signed numbers. So again, if you have to, you make do, but then you have to defining things like complex variables and how to work with them. Higher order roots. So it turns out that for higher order roots, there's not much of an issue here, especially if we're working only with a byte. Okay, so only the numbers 0 through 6 have a cube. So if you cube 6, if you cube 7, you will get a number greater than 255. So it becomes more than one byte. So in this case, for cube roots, all you need to do really is to check 6 values and see if those are you're given a number, you check if it's between this number and this number, it's going to be 5 is going to be the root, 4 is going to be the root, 3 is good, and so forth. You just check the ranges, and you can use that fact to take the root. So notice that when we're talking about the root here, the cube root, we're talking about only the integer portion of that root, okay, not the fractional portion. Also, we could also easily consider for cube roots negative numbers, because a negative number can have a real cube root. If we look at the fourth power, only the numbers 0 through 3 have a fourth power that's less than or equal to 255. Similarly, with the fifth power, only the values 0 through 3 have a fifth power less than or equal to 255. So you just check each value at the appropriate root. For higher bytes, we can again use successive approximation techniques, but I'm not going to go into that. So it's not so common to take roots. Square roots maybe, especially if you do something like Pythagorean's theorem, but higher order roots not so much. So if you need them, you can find on the internet, you can search and find algorithms for computing roots. So last thing I want to talk about in this discussion today is about integer ratios. Integer ratio. So it turns out that any real number can be approximated by a rational number. So again, a rational number is an integer over an integer. An approximation will always have a certain amount of error associated with it. But for many calculations, it's impractical to use full precision anyway. So again, the ratio consists of a multiply and a divide. And generally speaking, when we do this, we do the multiply first and then the divide. And the reason we do that is when we multiply, we expand the number of bits that's required. And then when we do the divide, in general, we contract. But we don't lose any accuracy. We use a lot less accuracy that way. So ideally, with integer ratios, it's nice to have ratios of small integers. And in particular, it's nice whenever we can to divide by a power of 2. And it's even nicer if we can divide by a power of 8. So basically a power of 8 means we can shift over by a whole byte. Okay, so if we can do that, that's awesome. It would be nice for the numerator and denominator to be factorable. That is, if I can factor it into pieces, then I can do smaller ratios and do a set of them. It would also be nice for the ratio to be really close in value to the thing it's approximating. That is, has small error. So let's take a look at an example. Let's look at the example of E. So E is this number, 2.718281828445. It goes on forever, and the bits don't repeat. I mean, the digits don't repeat. So that's E. It's an irrational number. So as an irrational number, it cannot be exactly represented by a ratio, but it can be approximated by a ratio. So here are some ratio approximations. Okay, so here are some ratio approximations. Here's the decimal equivalent of that approximation. Okay, so you can see how it compares with the original value, 2.72. Okay, so that's close. Here's the error. It's the 10 to the power minus 3. If I use this ratio, I get closer at 10 to the power minus 4. If I use this ratio down here, I get an error of 10 to the minus 6. So if that's acceptable tolerance to you, then that would be a good ratio to use. So these are just general ratios that give decimal approximations that are close to the value. We can also get ratios that involve powers of 2 in the denominator. Okay, so this ratio, for example, so you see that this ratio is simple and it has a power of 2 in the denominator, but it's not nearly so good as this simple ratio. Here's another fairly simple ratio that has a power of 2 in the denominator, and you can see that, again, it's not that great. Here are the errors associated with them. Here's a ratio. It involves two fairly simple numbers, and you can see it's definitely getting closer. Okay, 10 to the power minus 4. And here's another ratio that gives me an error of 2 to the minus 5. 2 times 10 to the minus 5. So we can get good approximations. Okay, so in general, that will require larger integers to work with. So there's a trade-off. You know, is this one good enough, or do I actually need to get that extra accuracy? Okay, so those are some issues that have to be decided by whatever plan you intend to use this for. Okay, so if I needed to use the number E, that's what I would use. What about the number pi? We know that's our classic irrational number. So we have this simple ratio, 22 over 7. Okay, again, it's 1 times 10 to the minus 3 accuracy. Here are some other approximations. Okay, I can get all the way down to 10 to the minus 2 times 10 to the minus 7 accuracy. Here are some ratios that are powers of 2, have powers of 2 in the denominator. So remember, powers of 2 are nice because when we do the division, one of the powers of 2 can be just a shift. Okay, and so that's really helpful. Actually, all of these would be shifts. So I would multiply by 201, and then I would do shifts associated with this. So this would require 6 shifts. Okay, 6 right shifts. Okay, and so anyway, the question is whether that's accurate enough, or this is accurate enough. Okay, so these are some issues that we need to work with in terms of this. So if I had, for example, 1 byte, could I represent or do some of these multiplications fairly straightforward? Well, with this one, it's not too bad because that's a byte. Okay, and I'm dividing by 8. So basically, I would take whatever number I'm going to multiply by pi. Okay, and so I multiply by 25. Is that result going to be greater than a byte? In general, it will be. So, and then we would shift back by 3 bits. And so anyway, that would be the process of taking a number and multiplying it by pi. So we can represent integer ratios, use integer ratios to represent arbitrary real numbers. Okay. So this is just another math trick that we can use in dealing with math. So there are lots of things, if you're going to start doing math, lots of things that you need to think about in terms of how to do the kind of math that you're trying to work with. And sometimes these things can get rather complex. Now, this is our first part for doing math. And we've talked about add, subtract, multiply, divide, and now we've talked about roots and ratios. So this is just the very beginning. When we come back next time, we're going to talk more about integer ratios or ratios and how we can use ratios to do different things. And then we're also going to get an introduction into floating point math. So that's what's coming up next in the second half of this. Thanks for watching.